All right, everyone, we're going to start our problem with our question. So we have material behaves like a metallic material. So we know that our Young's modulus is 100 times 10 to the ninth. We know our nu is equal to 0.3. Thermal expansion coefficient fills the whole cube. So it's open in the 3,3 direction, open in the 2,2, but attached in the 1,1. Final dimension is 3 is 1.54. So we know, we'll get to that in a little bit. Temperature decreases. Walls of the cubes are lubricated, but there is a shear strain that exists. So if we look at our stress tensors, we're definitely having a stress in the 3,3 because we see the arrows pushing in there. The temperature is decreasing, so the material wants to kind of squish back in, but it's also being pushed out there simultaneously because we're pushing in. It won't extend. It's attached to the walls in the 1,1, so there will be stress in the 1,1. It's free to basically move in and out in the 2,2s. There's no strain there, or there's no stress there. There will be a strain in the 3,3, and we actually know what that value is. The strain in the 3,3 will just be 154 times 10 to the minus 3 minus 168 times 10 to the minus 3. It will be negative 168 times 10 to the minus 3 meters. So that is our strain in the 3,3, so we know what that is. There will be some strain in the 2,2, and there will not be any strain in the 1,1 because we know that it's 0. There is a strain in the 1,3, so there will be stress in the 1,3. And we know now that we're in a plane stress state. So let's go ahead and let's start to set up our tensors. So I'm going to go ahead. I've already quit my notebook. We know that our Young's modulus is this. Poisson ratio is this. We are going from room temperature. So it's 5 minus 25. Final minus initial. Walls of the cubes. 2.7 times 10 to the minus 8, so 2.7. We know that our stress in the 2,2 is 0. Our strain in the 1,1 is 0. And this is going to be 154, 168, 168. Let's go ahead and start it up. So we are in plane stress. We're in plane stress in the 1,3 plane. We are not in principal stress, so we're going to have to figure that out, and then we're going to have to figure out all those rotations. All right, so let's go ahead and run this. What are our unknowns in this problem? We don't know what the sig11, sig33, and epsilon22. Sig11, sig33, epsilon22. Good. Solve for it. Strain in the 2,2 is positive because we have that force pushing down significantly. The material, as we push down here in the 1,1, it wants to expand out, so it's being pushed back by the sig11, and sig33 is negative. Excellent. It's all looking good. So let's go ahead and say that sig11 is equal to this. We know that our sig33 is equal to this. Shift enter, shift enter. Our epsilon 1,3 is equal to this. And then we also know E13, sig13. So our sig13 is equal to this. So that's our sig13. And then now we can go and so we need to do, we are looking at sig11. We're looking at sig33 and sig13. So we're not in plane stress, or we are in plane stress, but we're not in principal stress. To get to principal stress, and actually we need to just, let's evaluate these up here. Make sure your notebook's ready to go. To get to principal stress, I want to make sure that that new shear stress value is 0. And look at there, we've got a value. If we do this, this would be our sigma 1. This would be our sigma 2. And then that's our new shear stress value 0. Fantastic. If we were to just replace this, and then if we did, let's see, if we did, we already did a clockwise rotation to get there. So we would have to go from there to there. So probably plus 45. And that'll give us, excuse me here. Actually, probably be a minus 45. It doesn't like the precision there. There we go. Nice. But anyways, we'll see, and we can verify that angle in just a second. If I want to be in maximum shear, I'm just going to solve when the derivative is there, and you can see here it's either this or this. We could have done plus or minus, it didn't matter. So if I run in this direction, you can see same center. This is our maximum shear stress value. Fantastic. And then finally, it's asking us from the original stress tensor, 37-degree rotation clockwise. So that's going to be a minus 37. So T dot sig OG. And there you go. That's it. First problem, hardest problem done. See you next video. Thanks. Bye.